let's welcome Professor Russo give a talk, please.
Okay. Thank you very much, and happy birthday, Eli. It's very nice to be here. And the way to reduce the cost is simple. You find a killer app. So say telecoms or something, yes. And, well, it may come in the near future. Who knows? They may become a lot cheaper. Okay, my original title was, oh, you're missing the top again. I have a resolution problem here. Is this something we can fix? Got an expert here. This is not my computer, by the way, so don't blame me. Well, I'll keep talking while he's fixing it. I think the original title was Latest Developments in Photonic Crystal Fibers, and there have been so many different things and the time is fairly short that I thought what I would do is concentrate on just one of these, and this actually has to do with the hollow core photonic crystal fiber. And actually, I came up with a phrase which I just wrote down. Let me find it again. The kind of subtitle for this is "Gases Enter the Solid State." So we're all used to solid state devices and the wonderful things you can do with solid state. But the beautiful thing about a gas is that if you change the pressure, you can change its properties. So if you could somehow make it much easier to use gases, then a whole lot of new things become possible. And I hope maybe to show, at least point in the direction where this, in this kind of direction in this talk. So let's have a look. Photonic crystal fibers, first of all. No talk on hollow core photonic crystal fiber, at least, would be complete without a picture of Eli over there, looking very happy, as always. And the idea here, back in the early 1990s, I had actually worked a lot in periodic structures, and I knew all about stop bands and negative refraction, all the kinds of things you can do with periodic structures a long time ago. But then I got distracted into optical fibers, which was a bit of a distraction at the time, maybe. But then Eli came along with this wonderful idea that maybe you could create a three-dimensional photonic bandgap. Even two-dimensional to me was revolutionary at that time. I hadn't thought of it. I was kicking myself. So I was thinking, wouldn't it be nice to do something maybe with optical fibers and this new idea? And so I had this slightly crazy idea of creating a fiber which had a two-dimensional photonic bandgap, which would allow you, if it worked, to trap light in a hollow core. And I wouldn't have tried doing this, I guess, without the suggestion of Eli back then. You could ask, of course, even if you could make such a structure, why would you want to bother making it? So let's just have a look at that. One of the things this would allow you to do is to overturn the received knowledge about beams of light and how long the depth of focus, how long you can keep the light tightly focused before it diffracts out again. You can do the equations on this, and of course you end up with the depth of focus is proportional to the spot size, as Lord Rayleigh pointed out 100 years ago. What the hollow core fiber would do for you, if you could make it, would be to allow you to keep the light tightly focused over huge distances, which would only be limited by the loss of the fiber. So that if, for example, we were interested in maintaining very high intensity in an evacuated core, in an empty core, or a gas-filled core, the intensity times path length enhancement factor you'd get in a structure like this compared to a focused laser beam would be the integral of the intensity over the distance in the fiber divided by the same thing for a Gaussian beam. Turns out to be this factor, the vacuum wavelength over the loss in the fiber times basically the area of the core. And if you work that out for the very best photonic crystal fibers that we have now, 1 dB per kilometer loss at 1.5 micron wavelength, and a core radius of maybe 10 micrometers, you get an enhancement factor of 7 million, which is huge. And very exciting if you want to do nonlinear optics, for example, in gases, because you can keep the light trapped in a single mode with no diffraction and reproducible intensity profiles. But the key point being, most of the light, 99-point-something% of the light, is in empty space. It's in the empty core. So you can pump gases into the core and reap the benefit of that 7 million times enhancement. Self-focusing effects, which have been a problem in gas, nonlinear gas experiments, nonlinear optical gas experiments, are practically eliminated. The low transmission losses give you very long path lengths, And in fact, as it turns out, I'll tell you in a moment, you can control the chromatic dispersion and keep it uniform along the fiber, which allows you to play with soliton effects and all sorts of wonderful nonlinear effects that are well understood in conventional optical fibers. And finally, because the core is quite small, you can maintain high intensity for a given amount of power. You don't need so much power to reach the intensities to do some interesting things. So let me now talk about this idea of gases entering the solid state, sort of, and talk about pressure-controlled dispersion. I'm going to introduce one particular kind of photonic crystal fiber, which we call the Kagome lattice. Professor Noda will understand this. This is basically a basket weaving pattern, which was, I believe, can be traced back to Kyoto. It's basically a star. If you take a Star of David and you tile it, you end up with this structure. It actually turns out it doesn't have a full two-dimensional photonic band gap, but it has three very strong stop bands which almost overlap. They're strong enough to give you low loss, but the nice thing about the fiber is it gives you lowish loss over a very broad wavelength range. So if you want to operate with lots of different colors of light, different frequencies of light over a huge wavelength range, this is the fiber to choose, compared to the photonic band gap fibers, which have a much narrower transmission window, but very much lower loss. But here we have about a dB per meter or so loss. Okay, that's the fiber I'm going to talk about. If you manage to fill a fiber like this with gas, we could compare it with all those conventional experiments which have been done by such famous groups as the group in Gila, in Munich, Ferenc Krauss, and the team in Milan. These are people who fill capillaries with noble gases and put high energy, very short pulses in there in order to broaden the bandwidth. If you compare the loss of a capillary at, say, 800 nanometers, with a radius of the capillary, of the hollow region, of maybe 80 micrometers, which is typical of these experiments, you get a loss which, in order to get low loss, you have to go to large radius. If we go down to a radius of maybe 10 or so micrometers, the loss is just crazy. It's unusable. Whereas these fibers allow you this radius while offering low loss as well. So it's dramatic what you can do with this structure. So you can look in the literature and you can find the dispersion of the refractive index of argon gas. You can do a simple calculation based on work that dates back to Marchettili in the early days of fiber optics. And you can show that you can calculate very easily the refractive index of the different orders of modes that might exist in this core. The key point about this slide is that by controlling the pressure, and maybe the temperature too, you can control the contribution of the gas to the refractive index in here. And this is all very well characterized. One of the nice things, by the way, about argon, of course, and all the noble gases is that they have no Raman scattering, which is going to be important for what I'm going to show you in a moment. So we can tune the refractive index of the modes. And this is an example. If we take the fundamental mode, the single lobe mode that fits in the core, and we have a look at the dispersion as a function of wavelength all the way from 200 nanometers in the UV out to 900 nanometers. If the core is hollow, we have anomalous dispersion over this entire range. As we add more and more argon gas, 2.5 bar, 5 bar, 7.5 atmospheres, and so on up to 10 atmospheres, we can tune the dispersion over this range and shift the zero dispersion point over quite a wide range of wavelengths. Note the very low values, the relatively low values of dispersion that we have here. It's almost dispersion-free, but not quite. 1 picosecond squared per kilometer is about 1/20th of what you find in a conventional telecoms fiber. So we have a reconfigurable system in terms of dispersion simply by adjusting the pressure. This will, of course, also alter the nonlinearity. Right, so let's now have a look and see what the results of this system are if we launch short pulses in. So this is an experiment where we show the generation of deep ultraviolet light. So here is a length of this Kagome lattice fiber filled with argon. It's pumped in from both ends. You evacuate it first and then introduce the gas. The experiment is illustrated up here. We send in short pulses from a Ti-Sapphire system, amplified a Ti-Sapphire system, with energies of up to maybe 10 microjoules launched into the fiber. The length of is only a fraction of a meter, and at the other end we have diagnostics. There's a picture of the setup. The fiber doesn't have to be kept very straight. It's a waveguide after all, so the light can go around corners to some extent and come out the other end. So this is a movie of what happens when we increase the energy of these pulses from a small energy and increase it upwards. You'll notice that the fiber is initially dark, and then it's going to recycle in a minute, I hope. No. Let's see. The window's messing me up. You can notice it lights up at the end, and then the point where it becomes bright moves back along the fiber as the energy of the pulses increases. So whatever is going on here, these short pulses appear to be maybe temporarily focusing, intensity increasing to a point where something interesting happens, and we see the generation of ultraviolet and maybe even visible light at some point. And this point moves back along the fiber towards the launch end as the energy of the pulses increases. What was exciting for us in these experiments, which were actually a discovery in the laboratory, we noticed a flash in the fiber. We were looking for third harmonic generation, and we noticed this much more interesting effect where the light, the UV light, appears in the fundamental mode. Conversion efficiencies are really very high for a process like this, up to maybe 8% conversion experimentally. It's widely tunable, actually, it turns out. This band of ultraviolet light is pressure and energy tunable. If we change the energy of the pulses, change the pressure of the gas, we can shift this band of ultraviolet light right down into the vacuum ultraviolet, it turns out. There's a tuning curve measured very carefully by PhD student Kafai Mak in my group. You can tune over a very wide wavelength range and right, as I say, down into the vacuum ultraviolet. We don't have good measurements down there yet, but the efficiencies are really very high. Okay, so what is actually going on here? What does the fiber allow us to do? Well, the ability to control the dispersion very precisely over a broad range of wavelengths means that we can make use of the physics of dispersive waves into the ultraviolet. And let me explain a little bit about this. So this is a frequency wave vector plot of a dispersion curve, which contains, whether you use the wave vector versus frequency, this is the wave vector as a function of frequency expanded around some frequency. So omega is the deviation in frequency from that point. And of course, we have a term which is the reciprocal group velocity and the group velocity dispersion. So I'm just going to include the group velocity dispersion term here. And we get a curve something like this. Now, if a soliton forms, you add some nonlinearity, and a soliton forms, it turns out that the wave vector of the soliton becomes linearized. It's no longer a curve. The wave vectors of the different frequencies of the soliton lie on a straight line, and this is the classic soliton solution. So this now is the dispersion relation for the wave vectors of the soliton. You've lost the beta 2 term. It's been cancelled out by the nonlinearity. That's a soliton. Well understood. It's got a very, very clear group velocity, constant group velocity, and will propagate without distortion. However, if we add some higher order dispersion, as we have in the fiber, we add some higher order dispersion, some beta 3 to this, the curve will turn around. It doesn't keep going in one direction, it turns around at some point, and you notice that the soliton solution has the opportunity of overlapping, of phase matching in frequency and in wave vector with the free running waves. The non-solitonic waves are on this curve. The soliton is on this. And if the soliton bandwidth becomes large enough, you can actually shed energy into what we call dispersive waves that exist out here at very high frequency in the ultraviolet. Now, that relationship can be plotted in this way, wavelength versus the difference in these two wave vectors between the soliton wave vector and the wave vector of the free-running dispersive waves. And when they're equal, we're on this dotted line. If we do the calculation in the absence of any higher-order dispersion, this is what we get. If we add the higher-order dispersion, the curve turns around, and we get an intersection somewhere in the ultraviolet. But the beautiful thing about this is that by changing the pressure, nothing more than changing the pressure, we can shift this point, the zero dispersion point, over a very wide range and a very interesting range of the spectrum, right down to close to 100 nanometers, just by going from 1 bar to 10 bar pressure. Now, this is the reason why we get this ultraviolet light. You can run the generalized nonlinear Schrödinger equation with the correct dispersion that's in the fiber. and so on, and get very good agreement with experiments. We see the pulse entering with a relatively narrow bandwidth and frequency. The bandwidth slowly grows through solitonic effects as it's self-phase modulation in the absence of Raman scattering. And we get this massive explosion in the bandwidth at this point, and this is the point where the resonant radiation in the ultraviolet appears. What is actually going on here is driven, of course, by higher order dispersion. If we don't have any higher order dispersion, in that experiment we were launching an n=7 soliton, which evolves in a complex way as it travels, lots and lots of peaks. But the key thing is that the initial pulse is focused onto a very short duration quite quickly, and it's this point where the ultraviolet light is generated when you add higher order dispersion. And at this point, instead of just evolving as before, we get the ultraviolet light marching off at a different group velocity and with high efficiency of generation. Okay, so that is a tunable ultraviolet source, very high efficiency. There is no comparable source available out there. If you look for it, you won't find anything like this. But we've gone a bit further with this, and this is even more exciting to us, actually. We've been getting into ionization effects. Ionization of gases you associate with very high energy pulses and difficult experiments and self-channeling of light maybe in the atmosphere. If we have a look at the experiments that we're doing here, we could ask, could we get ionization of the gas at the temporal focus of that pulse going in as it gets shorter and shorter in time and there's bigger and bigger bandwidth? Well, it turns out that we can reach free electron densities of this sort of number at peak intensities of about 10 to the 14 watts per centimeter squared, which is the kind of value we achieve in the core of the fiber at the focus, at that temporal focus that I was showing you. And this can happen over length scales of several centimeters in a very beautiful, well-controlled way in the hollow core of the fiber. Actually, when Eli recently was in Erlangen, we had a discussion, actually, and I dug out some early papers where you actually worked on this stuff a long time ago, no? This was the early 70s. A rather different experiment, nanosecond duration pulses, carbon dioxide lasers, but you can see self-phase modulation of light in a laser breakdown plasma, which is what I'm going to talk about, at least self-phase modulation. In this experiment, what we have is a refractive index change, which is basically the Kerr effect minus the effect of the electrons when they're created, the free electrons that are created through the ionization process. And this is numerical modeling results. Initially, this is the pulse of light coming in. You can see the bumps. This is the envelope, and this is the underlying intensity, if you like, of the light. And you can see that the Kerr effect very accurately mirrors this bumping up and down, and it's always positive, as you'd expect in the gas. And then all of a sudden, when the pulse really becomes very short, a few cycles long, we get a huge increase in intensity, and the Kerr effect is still there, but you notice that there's a sudden surge in the negative direction for the change in refractive index of the light as a result of the plasma term. So we get this massive negative change in refractive index and in the gas, which has some very interesting consequences. These are some experimental results of the spectrum of the light as a function of input energy for a 34 centimeter length of fiber, 1.7 bar of argon. And you notice that we get the band, you can see the bandwidth exploding, and at some point where the bandwidth is maximum and the temporal focusing is also maximum, we see a shoulder of blue light, a blue shifted light, shifting towards higher frequencies as it moves out. And this is a signature of this plasma effect. You create higher frequencies as a result of the refractive index being very rapidly reduced in value. You can run numerical modeling on this. It agrees pretty well with the experiments. This is the shoulder of short wavelength light emerging at the temporal focus. And there are several cycles of this. As the input energy increases, we have another soliton, another one, and we get some temporal beating here between the different solitons that are created here. They are actually solitons, it turns out, and they're blue shifting solitons. So this is the first example of, you're probably, some of you familiar with the very famous soliton self-frequency shift in the presence of the Raman effect, where the soliton frequency goes to lower frequency as it travels. In this case, the solitons are moving to higher frequency as a consequence of the presence of free electrons and of ionization. If we switch off the ionization term, then there's no evidence at all of this blue shift that you saw in the previous plot. So just to summarize what we have here, the features of this kind of system, we can do ultra-fast nonlinear optics in a single-mode fiber filled with gas. The dispersion is adjustable. It's actually a very simple setup. It's a short length of fiber filled with gas. It turns out to be very stable with time, and it doesn't suffer optical damage. Gases are pretty good at coping with high intensities. And the ultraviolet light that's generated is spatially coherent. You could focus it down to a small spot. You can get self-compression of pulses down to a few cycles very, very easily in this system with no great need for a complicated apparatus. And we're able to shift nonlinear fiber optics into the ionization regime for the first time and actually create blue shifting solitons that are rejected through this ionization process. And some of the applications of this ultraviolet source, there's a list of possibilities. I'm sure there are many others. There are some technological applications, maybe to direct write in lithography, high resolution. And something we're looking at seriously is using this tunable ultraviolet source for the seeding of free electron lasers. And there's a lot of interesting physics one can do as well. Perhaps even, maybe in a couple of years, we will have high harmonic generation from just an oscillator, no amplifier needed, through self-compression of oscillator pulses even at high repetition rates. That's a very exciting possibility. All of which, of course, has been made possible by being kicked into this idea, partly by Eli sitting there. But of course, it wasn't that easy to make these fibers. But nevertheless, the photonic bandgap concept has made it possible for this to turn this kind of dream into a reality. So that's been very exciting for me over the last few years. And that's all I had planned to say. So thank you for...
It's amazing that you're reaching intensities of 10 to the 14 watts per square centimeter. In the old days, I tried to also get to the highest intensities. And to get close to that, I had to use especially very clean gas, namely the boil-off vapors of cryogenic liquids. Do you have to have some special cleaning of the gas to make it possible to get to such high intensities?
Not so far, no. We haven't had... I've read your papers. I noticed you make comments about keeping things very clean and so on. But no, we start with a very pure gas, and the fiber itself is very, very clean inside. It's been through fire, literally, to get into fiber form. So I suppose everything is very clean already, yeah. So we haven't seen any problems, no.
Right, and of course, the pulses are very, very short, so they don't carry that much energy to mess up the gas.
No, there's not a massive amount, no. That's true, yes.
Is there a possibility of reaching loss attenuation lengths comparable to single mode fiber in these kinds of fibers?
Yes. Yes, that was I did have a company at one point, and that was our goal, was to do that. But it's due to various mistakes by the CEO. The company no longer exists, but the technical team were convinced they could get down to at least to match conventional fibers. Although, of course, the hollow core fiber is a very different engineering challenge if you want to put it into a system compared to single mode fiber. So, anyway, yeah.
For the conditions that led to a negative refractive index shift that you described here, what was the carrier electron density in the
numbers? Let
range?
me, so I don't get it wrong. Let me go back.
Yeah, here. What is any?
This doesn't have a number, but I think this, you can rely probably on that number, 10 to the 17.
Yeah, so 10 to the 17.
Yeah.
Oh, that's very interesting. Yeah, that's comparable into doped semiconductors, or so you would see a far infrared plasma in that structure.
Something else you've worked on, I think. Yeah.